Good morning, I'm Akshay Saji and today I will be presenting on state space search, a fundamental concept in artificial intelligence. Every challenge an AI faces from navigation to gameplay is represented as a search problem. The goal is simple, find a path from a starting point to a desired goal. This entire set of possibilities is known as state space. By efficiently exploring the space, AI agents discover optimal solutions. Okay, let's get started. At its core, AI uses state space search to translate real world problems into a formal model. It can process. We break a problem down into states, which are snapshots of this situation, and actions, which are the legal moves that change the state. Think of planning a delivery route. Your current location is the state, and the driving to the next stop is the action. The collection of all possible locations and is the state space. Okay. The AI agent's task is to navigate this network efficiently, exploring the different paths until it discovers the goal state. This systematic and logical approach is crucial for achieving fast and reliable problem solving. Okay, let's look at what is the definition of state space. Let's clarify the four main elements defining the state space. They are the state space, goal state, initial state, operators. Okay, the state space is the entire set of every single possible configuration or situation for a given problem. Within it, the initial state is the starting point, and the goal state is the desired outcome. The transitions between states are handled by operators, permissible actions that move us from one state to another. For a concrete example, consider the 8 puzzle. Every unique tile arrangement is a state. The action of sliding a tile into a blank space is an operator. Okay, let's see the components of a state space search. The search process is managed using three essential components. First one is the search tree, then search node, and finally the search strategy. Search tree is the structure the algorithm builds where states are represented as nodes and actions are the edges connecting them. Secondly, a search node is the data structure that stores all critical information about a visited state, including the actual state configuration, its parent node, the cost incurred so far, and its depth in the tree. Finally, the search strategy is the core algorithm itself. The strategy is the intelligence that decides which node to explore next, dramatically impacting the search efficiency. Types of state space search. Search strategies are broadly categorized based on their knowledge of the problem. First one is uninformed search, and the second one is informed search, also known as heuristic search. Okay, uninformed search or blind search operate without any domain specific knowledge about the location of the goal. Examples include breadth first search, and depth first search. They are systematic but can be slow on large spaces. In the case of informed search, also known as the heuristic search, uses an estimated cost function, a guess of the distance to the goal, to guide the exploration. Let's look at the uninformed search more detailed. The three main uninformed search algorithms are defined by their exploration order. Breadth first search explores the search space horizontally or level by level. This approach guarantees finding the shortest path. Depth first search explores vertically, diving as deep as possible down one branch before backtracking. Finally, uniform cost search is similar to BFS but prioritizes the node with the lowest actual path cost from the start, guaranteeing optimality even when move costs vary. Okay, informed search algorithms leverage a heuristic function h of n to estimate the cost to the goal. Greedy search is the simplest, using only the heuristic h of n to guide its search. It's fast because it always picks the node appearing closest to the goal, but this often leads to non-optimal solutions. The industry standards is the A star search. A star uses the evaluation function f of n is equal to g of n plus h of n, combining the actual cost traveled, which is g of n, with the estimated cost, that is h of n. This balance makes A star complete and optimal, provided the heuristic is admissible, that is, it never overestimates the true cost to the goal. Now let's look at the application of state space search. State space search is the backbone of many practical AI applications. Pathfinding is the most common, where algorithms like A star power GPS, robot navigation, and in game playing, especially in adversarial environment like chess, we use techniques like minimax search to explore the game tree and determine the best move, assuming the opponent plays optimally. Search also solves classical challenges like the 8 puzzle and Sudoku. Furthermore, complex problems like logistics management and the operation of autonomous systems rely on search for planning, finding the optimal sequence of steps to achieve a goal. Even tasks in natural language processing, like parsing sentences, use search principles. Let's look at some of the advantages and limitations. State space search offers significant advantages. First, it provides a general framework by modeling any problem as states and operators. We use the same set of algorithms to solve widely different problems like route planning and resource scheduling. The search provides a systematic exploration. Unlike trial and error, algorithms like A star ensure that a solution is found if one exists, giving reliability. Most importantly, it allows us to integrate heuristics. This informed guidance lets the AI focus its resources on promising paths, drastically cutting down the search time and making complex problems solvable in practice. Okay, despite its strength, state space search faces three main limitations. The most critical is combinatorial explosion. This problem complexity increases, the number of possible states can grow exponentially, making it physically impossible to explore the entire space, even for supercomputers. Second, the efficiency of informed search is entirely dependent on the quality of heuristic. Poor heuristic renders the search nearly blind. Finally, these methods struggle with continuous state spaces, where states like the precise angle of a robot joint are not discrete and countable. In conclusion, state space search is more than an algorithm. It is the conceptual foundation upon which classical AI problem solve is built. It provides a rigorous universal language, states, operators, and goals for translating any challenge into a solvable problem. We have seen that the key to modern efficient AI lies in the strategic combination of systematic search strategies with informative quality heuristics. This framework continues to be essential for developing intelligent and reliable systems across robotics, planning, and gaming. These are some of the references You can check it. And finally, thank you for listening.